Hi, I'm Gray Yellow with Cuesta College, and today I'll be talking about block ramp systems for Physics 2A students. The first block ramp system you're going to see is going to be without friction, both in the class, in the book, and also here. It's the easiest system to analyze. You just take away all frictional forces, take away anything else that might be complicating it. And the most important part about this is how you draw it. Now, a lot of you might not really want to draw things. You might just want to start plugging in numbers, but it's really important that you get in the habit of drawing things and drawing them large. Maybe not as large as it is on this board, of course, because you would run out of paper really quick and use up a lot of tape, I'm sure. But you want to draw them as large as you can without getting in the way of your work, because it allows you to label things really easily and really understand what you're doing. So let's start off with just labeling what we have here and labeling our axes. So we want to label this with an M, M1, whatever. And now you might be thinking, oh well, this is X, this is Y, and that's a really, it's a common way to label something. But we're not going to want to do that in this case. Whenever you see a ramp, any type of ramp system with a mass, pulleys, whatever's going on, you're going to want to relabel your axes. That's going to seem kind of weird, but that's what you're going to do. So, for your first exam, you will probably have, you'll definitely have at least one problem like this, whether it's free response or in multiple choice. You're going to have something like this, and by that point, it'll probably be involving friction. But you want to start here first. So first thing you do is label the axes. The X is going to be on this surface. It'll be parallel to the surface that it's moving along. And Y will be perpendicular to that surface. Okay? Now we're going to label what's happening here. We have mg pushing down, and there's going to be some acceleration down here, right? It's going to want to pick up speed and keep sliding down this ramp because there's no friction. We're assuming that this is a frictionless ramp. This thing is just ice. So we're also going to have a normal force. So we want to figure out what those are. Now the convention is to make these your X and Y axes, and then to reconfigure everything else around that. And so what we do is we take the triangle we already have, and we draw a new triangle. For this, this line is going to be perpendicular to the surface, and this line will be parallel to the surface. Now if we took this triangle out of here, and we spun it around, we made it bigger, and we brought it over here, it would be just like this triangle, but facing the opposite direction. This triangle is basically a smaller, twisted mirror image of the big triangle. And sometimes I see people getting messed up, like, how do I draw my triangle? Do I want this to be the 90 degree or that to be the 90 degree? And it can be a little confusing. But I want to come over here and kind of use what I said in the tips and tricks video, which is, does this make sense? So we're gonna come over here and we're gonna see if this actually makes sense. So if we have a really shallow triangle, there's going to be a really really small acceleration on this. This is not going to pick up speed very fast. So we're going to draw mg straight down, and let's say we drew this triangle like this, and we got it wrong. We made this our 90 degree angle. And so here's what we're doing. We're making this. Now you're going like that. Okay. We messed up, and we want to see if we what we're doing wrong and how we did it wrong. Well, all your components have to be parallel or perpendicular to the surface, because we made them all in the x and y plane. But this guy, we know this guy is not, it cannot be parallel to the surface. So we know that we've done it wrong. We made a mistake here, because we see that this 90 degree cannot be. If we tilted it up, then it would be 90 degrees, right? So that's one way to remember if you drew your triangle correctly. So all this is saying is that one component is going to be pushing this mg, this mass, straight perpendicularly into the surface, and another component of mg is going to be making it slide down the ramp. And we know that that since it's just sliding down the ramp and it's not sinking into the ramp this way, and it's not jumping up toward the sky, we know that the sum of the forces here has to be 0, since there's no acceleration. So we're going to draw a normal force. I like to label Fn, and some people label just n in engineering classes and physics classes as well. Sometimes they just say n. But I like F sub n. And so now we've drawn our triangle correctly. We want to see what these components are. And since you guys have gotten used to components by now, we can just say that the opposite is mg sine theta, and the adjacent is mg cosine theta. Okay? Now to see if this really makes sense, we can go over here and do the same thing. I'm going to make this just a little more perpendicular so it looks a little better. There we go. Also a little more accurate. And we have a normal force. And so this is going to be mg sine theta and mg cosine theta coming down. So we see that our sum of forces in the y equals 0, equals the normal force minus mg cosine theta. And we want to say that the sum of forces in the x direction actually do not equal 0 because it is moving. So we'll say that the sum of forces in x is going to be equal to mg sine theta, which is going to be equal to ma. Sum of forces is always mass times acceleration. And we have a very real acceleration, so that means we have a real sum of forces in the x direction. And you want to really kind of look at this, and the reason why I drew such an extremely shallow triangle is to see, just the relationship between these, and make sure that the cosine theta and the sine theta portions make sense. So if we had say no incline, that means that theta here would be equal to 0. So the acceleration down this ramp would still be equal to mg sine theta, but mg sine 0 is mg times 0, which is just 0. So it doesn't go down the flat surface at all. It doesn't accelerate at all. And if we had this equal to mg cosine of 0, the cosine of 0 is 1. So the normal force would just be equal to mg, which is a flat surface. we will really want to ask ourselves, does this make sense? And that's a cool question you can ask yourself in physics. A lot of higher up math, it's going to be not always, it's going to be really abstract. And you can't always ask yourself, would this happen in the real world? I mean, you know, visualizing an eigenvector or a Taylor polynomial is difficult for most people, but including myself. But you know, when you draw something out like this, you can actually see what's happening in the real world and ask yourself, you know, would this happen in the real world? And you can say, yeah, I imagine that a flat surface with angle 0 is going to have no acceleration. If I put something on a flat surface, it's not going to move at all. It's just going to stay right where it is. And that should make sense. So when you're drawing a block ramp system with no friction, it's really important to draw it big, number one. Number two, label your axes. You get points on free response tests for not just getting the right answer, but how well you show that you know what you're talking about. So labeling axes is super important for Physics 208A. It's really critical. You may have a lot of this stuff going on in your head and may be able to just pump out answers like it's no problem, but your teacher really isn't going to care unless you can show how you did it. So be very clear. Always label your axes and label all your forces. Okay, what's going on in the normal force? A lot of times people forget that this is actually a force, and then break things up into components. And if you can do some of the forces in the y, some of the forces in the x with no friction, then friction should be no problem. We're just adding in a couple more things, and that's it. So that is the block ramp system with no friction.